Test. Test. Welcome back. Another day of Bayesian Cognitive Modeling. We're making our way through the case studies here. We yesterday finished up signal detection theory, and today we're going to be going through psychophysical functions. Yeah, so if you're new here, go check out some of the other videos, of course, to get more of a context about what we're doing here. But essentially, it's just we're doing all the exercises in this textbook, Bayesian Cognitive Modeling, in order to facilitate developing some understanding about how to do or conduct Bayesian inference in the real world, and how could I go about conducting. So how would I go about implementing these things, and what sorts of things are the crucial components if I were to go and try to interpret some of the findings, and what sorts of common problems I might run into when trying to implement these things across various softwares. But here we primarily focus on using JAGs. But maybe I can crack open some stand code today. I am notorious though for sometimes doing the stand code. Either way, let's pull up the example today in the book, and then I'll get started. There it goes. Oh, perfect. It's already open. Right. So psychophysical functions. Here, psychophysics, if you're not familiar with, it gives a little brief sort of synopsis about what's the big questions regarding what we're interested in psychophysics. And that really is trying to understand or how we can measure a physical stimuli and infer things about internal states, like related to psychometric properties that we're interested in, like attention, memory, and stuff, perception, for that matter. Right. So it's creating that map, which, in my mind, it's almost one of the most purest forms of psychology, where when you get down to it, a lot of what psychophysics is interested in is that basic science that a lot of applied findings throughout the literature, specifically in the cognitive psychology, are interested in researching. Thought I heard something. Anyhow, so it's just describing one of the many possible common paradigms that one could conduct if they were interested in doing a psychophysical experiment. Let me open the example code then before we move forward here in JAGs. Okay. Data. Oh, nope. Case studies. And now we're doing psychophys. Oh, sweet. And now we're just going to set the working directory here. And we're going to crack open some sources. And I'm just going to open the first example, but we're going to contextualize it before I discuss any of the specifics about it. Oh, and this one's going to involve, looks like writing some code because it has answers in a separate code. Great. All right. So we have logistics cyclic function. All right. Okay. Alright, so let's get into it. So in this example, we're going to talk about an experiment concerned with time perception here. And this is going to help demonstrate some of the crucial concepts, that being this sort of psychophysical function here, as well as some of the characteristics that we can infer from the data based on this function here. So in this case, from my understanding, I'm not critically familiar with this, but once again, we learn along the way. So here we're just demonstrating what is the relationship, what's the theorized relationship between stimulus intensity and the probability of that someone chooses one option or another. And what we theorize then is that it follows this sigmoid distribution where the response probability here at the halfway mark, which would be, choosing one response or the other, is equivalent to some given point on the stimulus intensity. So at some intensity of whatever stimulus we're looking at, it's likely that it's most likely someone would choose either or response randomly, essentially, right? However, there's also another interesting characteristic of the sigmoid function that we'd be interested in, and that is called the just noticeable difference here. And the just noticeable difference is the maximum point to which on the sigmoid function that maps to the highest point on the stimulus intensity that a subject identifies a given response, or is most probable that the subject would identify the response. And this stimulus intensity then is a reference sort of characteristic where 0 represents a non-difference from the comparison. So I guess to further just contextualize this more, in these sorts of psychophysical experiments, subjects are given 2 stimuli, of various sorts related to types of sensation. And then we have this sort of control stimuli, and then another stimuli which we vary from trial to trial. So in theory then, as we vary from trial to trial and people give their responses, this allows us to build individual curves representing these points that we're describing here. The point where the subject would choose one option or the other at about 50%, which is the point of subjective equality, and then the maximum point here, this just noticeable difference. So just noticeable difference? Okay. So for this particular experiment then, we're going to be looking at 8 subjects who completed 3 blocks of 80 trials. So 240 trials in total, and each trial had 2 beeps, of different durations, it looks like. Okay, so I had 1 beep that lasted 300 milliseconds, and the test beep was variable. So we get like a beep, and then a beep, or beep, beep, So we're asking if subjects are able to differentiate between the 2 stimuli, and we're going to be able to then estimate these curves for how accurate a subject is at capturing differences between the 2 stimuli at various stimulus intensities. Great. In addition to that, we also, in this particular experiment, took a adaptive staircase routine. So I don't know what an adaptive staircase routine is, but it seems like it's a way to which we it's just essentially a way to which we change the stimulus intensity on the basis of how accurate a given subject performs. So if a subject's performing poorly, we're not going to make it harder. It's going to change with respect to the performance of the subject. Right. So here then shows test intervals for the proportions of trials of which subjects responded longer. Okay. So here's the subject, and then 200 trials. So we have like 2 blocks of trials. We have some interval of trials. And then we have this probability of response. And you can see then, if we have this theoretical sigmoid function that we think everyone follows, you notice this same distribution here across 8 subjects. Some people following it quite nicely, while others differing in terms of the peaking of the curve, as well as the what's the word? I can't think of the word I want to use. The curviness. Just describing that, this is not a linear sort of relationship here. Or it could be a linear relationship, but it doesn't follow a linear function here. Now, one thing to note here is that given that we're theorizing that the psychophysical function for this particular task follows a sigmoid distribution, we can approximate that using a logistic function. So that's something comes to mind and might be pertinent to what we're going to see in the future, right? Because this is like a common thing, and this is the common case made for why we do a link transformation, or why we use a link function for problems related to binary responses. And it's that the distributions of the responses have to be restricted to this range. So if I use a linear distribution, then I can go out of these ranges, or I can get predictions out of these ranges. So sigmoids have these like asymptotes. And that would be my interpretation at this point of why this might be a nice case, other than some of the theoretical reasons why we might choose this sort of typical S shape. There's probably history to it of sorts. Right, so this is our hypothesis, right? This is our theorized data generating process follows this sort of distribution, which here maps onto a logistic function. Which looks like so. Right, so if I took logs of this and then logit function here, this is what will you get? We have alpha, beta, and then the average of the responses subtracted from a given test duration for a subject at a given trial. So now we're going to look at the graphical model here. Do we have the graph? Great. Okay. And it's trials. Okay. Look, one more thing. It's R. So when a subject decides that the second tone is longer than the first, then we get this. We get this value for that given trial. Okay. So here's the total number of trials, and we have this plate here, so J intervals and I subjects. So intervals here represents the pair of stimuli between the first beep and the second beep. So we have some set of intervals, and with across all those intervals, we have information about each of the subjects, right? So then for each set of intervals, we're going to have a value here, which, if I'm not mistaken, ends up being like 240, right? So J is equal to 240 or something. We'll look at it. And then we have subjects. So each subject for each of the intervals is going to have some count here. This count could be the same value for all subjects. In this experiment, it is. And then we have this value, which is how many times a subject says this particular interval is longer. And then we have X, which represents each time a subject testoration. What is testoration? All right, because we did an adaptive test, it's possible that the tests are longer or shorter for a given subject. Eight subjects, 28. What does N then? Is time? It looks like it's how long the experiment is. It might be so. It's possible that X represents length of experiment here. Like length till response. Like RT or something. But that wouldn't be continuous. Wouldn't that be continuous? I mean, well, I guess not. If we just, for each subject's trial, we have some time it took them to respond. And then we have some number of trials, and of the ones that they did respond, we have this we have this time associated with the longer responses. Okay, yeah. And we're going to learn about this coefficient here, which is going to give us the log odds of choosing an option for for a value of duration. So this is going to tell us the contribution of the duration to predicting the probability of choosing an option. So using those values, we can estimate this rate of success or something. But for each subject, so we can get these rates for each given trial in a subject, which is cool. And then we have this random effect structure here where each subject is going to have these terms, and we have averages of these terms. So each subject then is distributed from a Gaussian distribution here with mu sigma. And alpha beta are respect the intercept and slope terms for the logistic function. So this is the average starting point and the contribution of the stimulus duration to predicting this. What do you think the function theta lim construction in the Winbook script? Let's take a look. Theta lim. The theta lim is equivalent to the limit. Oh, so we're getting like the optimized value for here. So we're generating all possible values for this, and this is sort of giving us the maximum likelihood almost. It's like give me the minimized value of this many possible values, and the maximum. So min and max, where the maximum goes from this to this. So we're setting limits so that it's not from like what's the word? Extend out to infinity. Right, so this is our approximation for the given value for theta. Which we use in the logistic function. Right, and we get one of these functions for each subject. Oh, and RJ. Oh, something to note here. RJ is distributed by so this count of long durations that we observe in the data is distributed by the number of points times trials for that given subject, and then the success rate for a given trial. Having observed the data for having observed the data. Let's back it up. So for each subject then we have a set of trials, which because of the adaptive testing these things can vary, right? So there's going to be this distribution of long intervals, which we believe is binomially distributed and with parameters n, which can vary per subject, and theta, which can also vary per subject. Theta being the success rate here for observing a long duration. So that is representative of the sensitivity, right? And then to fit the logistic curve here, we take the logit of this parameter. So this gives us the sigmoid function, right? But to do so, we need a specific minimalized value from each of the distributions of, or from each of the this is the sigmoid function we put it into, but in order to get this, we first describe it in terms of this, where we take the mean centered of the beta. So we set up the logistic regression here, and then we use the link function. So we put a sigmoid function on it after we first restrict the range, right? Because this value can go to infinity. So we restrict the range, making this to ensure our approximation is implementable in the software. And then once we have that, now we're going to get distributions for each of the parameters within our logistic regression here. And we use a random effects, a hierarchical structure. So we're going to get averages for both of the parameters, sigmas for both of the parameters. And because we're in JAGs, we have to do the lambda parameterization. So that's why we also do the here. Okay, so let's go ahead and run this. So we get loads of plots, RPORP. So these are the probabilities. So what's RPORP with respect to R? Nothing. And then we have the means, number of stimulus for each of the subjects, number of subjects. I guess the question here is why do we need RPORP if we're not using it? It might be for another problem. But for this particular one, we're loading those data, and it looks like we're going to have 3 chains, so we initialize all the parameters, which we set priors for. And then we're only interested in alpha and beta because it's going to give us the intercept and slope term for the long duration coefficient, and then we'll run this first model. It is. Maybe it says working directory. And no, let's see. Node 422 inconsistent with parents. So it says it might be something with the parameterization used for the JAGS code. So Mm. Mhm. It has to be something with the so setting the initial value actually broke the code, it looks like. Or setting the seed made the nodes inconsistent. Mm. I see. So it's something in the initializations. So what's happening here is that the value that I'm giving for one of these initializations is a value beyond the range of possible values that I specified here. So if I make all these 0, mm, I mean, it works sometimes. So what do we get out of it is we get alpha, betas for each of the subjects. And the chains look pretty mixed. Nice. Subject 8. Let's see what subject 8 looks like for this one. I'll just go, okay. So maybe we just go and look at subject 8's data. 6, 6, 6, 6, 6, 6, 6, 6, 6, 6. And then the number of trials for subject 8. 6, 6. It might be something with their data in particular. But here we get the curves, right? So here, then we have the test interval, right? So the probability of identifying a response as being a long response, and then we identify the point for each subject corresponding to the corresponding to the just noticeable difference point. And then we also have the 50% point for each subject here. And you can see that it looks like the sigmoid function model fits well for some subjects, but not for all subjects. So it's good that we chose to use a hierarchical structure here, because you can imagine how if we didn't, subject gates estimation could look even worse. Right. Alright, so let's take a look at the assignment then. What do you think this function does? Well, like I described, it's like setting minimum maximum like restrictions on the possible values for what lambda or theta can be. It's like a constraint, making it so we don't get like infinite values, maybe. That would be my guess. Okay, so what we see then is, I was looking at the common answer and check my answer against it. So the construction, so theta lim constructs or prevents the logistic function from taking on extreme values that would cause error, right? So us to identify unrealistic results. So anytime you work with a probit or logit model, you might there's a chance to obtain these sort of undefined real results. So what we do here then is a way to prevent the undefined real results from occurring in using the Gibbs sampler by just restricting the possible distribution for theta in this case to not include extreme values, guys, and that's fine, or it seems to be working out fine. Like we still get like fairly reasonable estimates, reasonable in the sense that they seem to be predicting or mapping onto the subject response data nicely, and I'm not sure how we generate these sigmoid curves. Let's see. So if we take alpha beta here, alpha map each subject. So we set up some containers for the alpha and beta parameters then, and then what are these? So for 20 trials, 8 subjects. So then we're gonna get the density for that specific point for each subject for both of the parameters, and then we're also going to select a sample of possible values for each subject for each point. So then you end up with alpha map and beta map, which are these density distributions for each of the subjects. And then alpha cell, let's see. Alpha cell then is going to be the 20, or for each subject here, I think we'll give 20 observations sampled from the subject. And now we write the psychometric function here in the code. So the psychometric function takes on x as so it takes on the map estimate. So the The map estimate is it talking about the PSE? Anyway, it looks like we take the exponential of our distribution over 1 plus. So we're essentially logistic function for the given subject. And then we have our part is inverted. Function for all the posterior alpha betas uses to calculate J and D posterior. So here's how we calculate the J and D. And then the inverted J and D. And then function for 20 grabbed posterior and alpha betas. Use this. Looking for where F3 is used in the code. F3 is not used just yet, it looks like. But it might be part of the exercises. So we've identified what the first thing does is that restriction for values. So the sigmoid curve in 12.4 are single lines derived from point estimates. 6.4. There we go. So we derive the psychophysical functions from the point estimates, right? To visualize uncertainty in the psychometric function, we could use intervals. We could have like a credible interval. So since this is a Bayesian problem, we could. I'm not sure if it's common practice to have a shaded sort of credible interval that surrounded our sigmoid function. And graphing, maybe that's common, but let's see. Graph Bayesian graphs, credible interval. Shaded. Okay. So yeah, it looks like people do it. You get like the 95 probability confident or credible intervals for distributions and put them on graphs. So you could do something like that in this case. So sort of like a confidence interval, but more easier interpretation. Hmm. Oh, well, another way to estimate uncertainty, we could use posterior predictive checks, right? Where we estimated we use the functions that we estimated and then plot just plot the points for estimates using the intercept and slope terms that we got for each subject. So we can just sample those and then plot all the points. Or something like that, maybe. They're nice. Okay. So it's something to do with sampling from the posterior distribution, the joint posterior distribution between alpha and beta, and in doing so, getting a range of possible values, a range of possible curves for a given subject, right? And it looks like the answers portion here is actually contains the visualizations. The visualization generated make clear about the additional information that is brought. So if I were to come here, this is supposedly just giving me the additional information gathered. I see. So what is this then? So what we're doing is we're taking possible values from we're sampling from the joint posterior distribution of alpha and beta instead of taking the average one, right? So this is the average estimate for alpha for a given subject across the trials, and this is the slope term for beta. But we could, in theory, sample jointly from those two distributions and then create several curves. Or you could just use all of the trials, but we don't have to do that here. We can sample like 1,000 trials and then just get these underlying values to see if, or to get a sense of how much uncertainty surrounds the estimates for, or the average estimate for our alpha and beta parameters. And then it also just gives you a sense of like how much of the data that we saw in the spread still fits along some of the possible combinations of parameters for alpha and beta. So the possible sigmoid distributions for each of the subjects. So thicker curves here would be indicative of there being larger amounts of uncertainty with respect to a particular estimation for a given subject. This is just to say that more concretely then, if you take a look at subject 8 here, we see that there's a lot more variability surrounding like alpha as well as even beta here. And so, given that, you see that it's a lot thicker in terms of like the possible values. But you can see that some subjects, while they have variability in the slope term, they don't necessarily have as much variability in the intercept. Right, so here we have pretty tight intercept here. Extremely variable intercept, very tight, and then we have a lot more variability in the slope. And then here you can even see that it looks like we approximated like a linear relationship almost between the two. So it looks weird. I don't know where this curve's kind of. I mean, there's obviously not a linear. It's not a. It is a sigmoid function. It's just a very altered one. So it may seem. In addition to that, we can also just take a look at the posterior distributions for. But this is not the posterior distributions for the. This is okay. This is coming up in a soon-to-be question. So compare subject 2 with subject 8. Oh, let me pull that up. Subject 2, you see that the sigmoid function accurately captures the patterns of responses for them. But while if you take a look at subject 8, you can see we have this sort of inflation in identifying longer responses. So, and we weren't able to capture this inflation using a sigmoid function, or it doesn't seem like we would. And yeah. So one of the aims in the analysis is to use psychometric functions to infer the just noticeable differences. So figure 4, 12.4, where is it? Okay. In figure 12.4, just notable differences are indicated by the difference on the x-axis between the dashed line and the corresponding 50 and 84% points on the y-axis. I don't know why 84% is the just noticeable difference, but there would be a dashed line there, it seems. I think I actually generated this plot though over in the other script. I'm gonna have to run it a couple times. There it goes. Plot. Cool. Alright, so you take it here. So these are the just noticeable differences then. For each subject. The predicted just noticeable differences. I'm just going to look up this term. And I'm going to try to just think about it more so I can contextualize what we're actually interested in here. Just noticeable. Number which is below. Right, so things below the just noticeable difference are presumably not explicitly perceived So this is a way to quantify perception. So below this threshold, it's theorized that people are not cognizant of it. So just noticeable differences can vary as a function of the task type or sensory domain we're interested in. In this case, we're talking about sound, and just noticeable differences then we start to note there are just noticeable differences, it looks like, for intervals of sound around 350 here. So the sound has to be this much longer in order for people to notice there being, or indicate being more likely that to indicate that there being a difference between the two sounds that they heard. And that's useful in the real world. You can imagine that we wouldn't want to make sounds, or we could use that as in the real world. I can think of two cases where if you had to generate sounds and you wanted these sounds to be perceived as similar, then you had this sort of range of possible sounds, duration. I'm holding other things constant, of course, but it's possible people might not detect the difference in the sounds if you kept it below the range that was described here. So if you had some general sense of what the average detection rate was, or just noticeable difference rate was across subjects, which it seems we do here. These are the posterior distributions for the just noticeable differences in milliseconds. So it's the value from 50% to 84% in this case. And here is the difference. And you can see it can vary substantially across subjects, with some having higher just noticeable differences and others having lower and quite precise distributions of possible noticeable differences for this particular task. So that's cool. Plot posterior distributions for just noticeable differences and interpret the results. Which subjects are better at perceiving differences in time? So, like we saw, how do we estimate the just noticeable differences though? So here, we built functions to do that, right? Or functions were built for us to do that. Function used to calculate just noticeable differences. So we use this F2 function. And we look at the answers. Where do we get just noticeable? Oh. So to calculate just noticeable differences, we take the inverted posterior distributions for alpha and beta. We set some interval. So we're taking here exponential of the distribution of mean centered here with a given beta alpha beta over 1 plus. And that was also described, I think, in the interval sensitivity thing that I just looked at in the wiki. Yeah, so change in y over I. So change I over I is equal to the k. Efficiency required change to C. Where I is intensity, right? So if we have intensity, change in intensity is equal to k. K is some constant. So we're taking the exponential of the value over 1 plus the exponential of the value here. And that is for the x's, and then we can do this. Oh, I see. Negative y. Negative y minus 1 minus the baseline. So we have the probability, the predicted probability of not choosing the option over 1 minus is not choosing the option. Choosing the option, and then the log, and then we remove the baseline and divide this whole value by the slope. And then we get the difference between calculating the posterior for alpha and beta, the joint posterior for alpha and beta. We can get the point estimate at a given value for a given subject, and then we take the difference. In this case, we use this threshold, and we get the just noticeable difference. Okay. And so if we take the density of the just noticeable differences that we calculate for all subjects, and we just plot those, then we'll have the overall differences between 50 and 85 for each subject, and it looks like, who does it want me to refer to? Which subjects are better at perceiving differences in time? So subjects that are better at perceiving differences in time would be able to identify values the point of subjective equality, and just noticeable differences would be closer to one another for subjects who are better, I believe. Right. Okay, my intuition's correct here, where if you had a just noticeable difference that was closer to the left of the axis, then that would indicate better performance. Or those are better subjects because they're more capable of perceiving smaller differences in variation from the beeps. Right. So just taking a look at this, estimates that are precise are better here, and then estimates that are to the left are better with respect to being able to perceive intervals that are smaller. So small changes in small deviations from between the stimuli. So subject 7 is the worst, and subject 2 is really good, if not the best subject. Or subject 5 is the best subject here. It's the closest to the left. We can also just that's too big of a matrix. Maybe 23, 23. Yeah, 19. Right now I'm just looking at the left tail of the distribution, and it looks like subject 5 is the lowest, and then 52 is the high. So the only other candidate, 23 and 65 is 2. So it looks like subject 5 is officially the sickest perceiver of sounds. Look closely at the data points that are used to fit the psychometric functions. Are all of those close to the sigmoid curve? And how do you think the possible outliers would influence the function? Well, some of the points used are not close to the sigmoid function. And bias in the sigmoid function, like here, like so, you can see is going to influence the curve. And if the curve moves, so if the curve shifts leftward, like in this case, as it would be more rightward in other cases, then we're inflating or we're deflating the potential just noticeable difference between here and here. So we're getting biased estimates in the just noticeable difference in part of points skewing the distribution of our sigmoid curves for a given subject. So this is particularly of importance when we have subjects like this, like subject 8, I think is a really good use case for that situation. Right, so in other cases, though, you can imagine that, like subject 4, geez. So this black point, subject 4, you can imagine is skewing the distribution of the difference here, thus making the curve, in this case, we would be inflating the value of the just noticeable difference here because we're making the value shifts here, like the curve shifts. Also, subject 7 is like not really good at the task. And so, it's possible that there's also bias in their just noticeable difference performance because of how poorly they performed in the task. So it might be, in this particular case, it would be important to incorporate some sort of exclusion criteria where if you fail to perform accurately on some X set of trials, you consider excluding the subject in entirety because you're less likely to get, or you're more likely to get a poor estimate and thus a poor approximation of the just noticeable difference. Great. So that is the last question here. So we're going to stop there for today, and we're going to move into considering contamination here in the next example. And we're going to continue with this particular psychometric function, but now we're going to extend it to consider other issues that might arise when we are trying to capture this sort of data. So Right. So I'll look forward to going down that contamination venture with you tomorrow. And thanks for sticking around. I hope this was informative. Yeah. So have a great rest of your day.